Hello, everyone. I would like to welcome you to this day of conference. And we begin today's program with talk by Pilar Páez Guillán on the lattice of restricted subalgebras of restricted Lie algebra. Pilar, if you could please try sharing your screen.
Okay, thanks. I think I'm sharing now.
Yes,
Yes,
it can be
okay.
perfectly seen. Thank you.
Great. Let's try to here. Okay. Well, good morning. Well, morning or whatever to everyone. First of all, I would like to thank the organizers for letting me give this talk, and also for organizing the school itself. I'm a student and I'm learning quite a lot, so thank you. Okay, I'm going to speak about a joint work, two joint works really, with Nicola Maletesta, Salvatore Siciliano, and David Towers. And the title of my talk is on the lattice of restricted subalgebras of a restricted Lie algebra. So, although I am positive that many of you already know what I'm going to talk about, maybe some others not. So, let me begin by Let me begin by explaining what I'm going to talk about. So, what is a restricted Lie algebra? Which will be the main object that we deal with all along the talk. So, a restricted Lie algebra will be a Lie algebra, but over a field of positive characteristic, and moreover of the structure of Lie algebra, we're going to have a unary operation, which we call P map, and we denote but this P between brackets, which must behave well with the rest of the structure of the Lie algebra. I mean, with the product by scalars, with the sum, and with the bracket. So the product by scalars, just what the P map does is to take out the scalars back to the P power. In the bracket, it also behaves quite well. If I do the bracket of an x to the P and another element y, this is the same. This must be the same as doing P times the adjoint operation of x on y. And also we have this relation with the sum, which is the most tricky of the three. Instead of, well, what we would desire to have this x plus y to the P, xp plus y to the P, we will have an extra term here, okay, which has kind of a more tricky definition. But, well, let's just think about it as extra terms, a sum of extra terms, which vanish if the Lie algebra is abelian, for example. If they're restricted, the Lie algebra is abelian. Okay, so this is a restricted Lie algebra, and we're going to speak about its lattice of restricted subalgebras. So, what is a restricted subalgebra? If I pick a subalgebra H of my Lie algebra, I'm going to say that it is restricted if it is closed regarding the P map. I mean, if I pick an element H of the subalgebra, every time that I consider this P map acting on H, I'm still on in the subalgebra. Okay, so the restricted subalgebras of a restricted Lie algebra, together with inclusion will form a lattice, okay? In which the meet of two elements of two subalgebras is just its intersection, and the joint of two subalgebras will be the restricted subalgebra generated by them, which is, of course, the smallest restricted subalgebra containing H and K. And I'm going to denote it with this notation, these two angles, and this subindex property. Okay, so once we know what are we going to talk about, which are the elements of this talk, what we are willing to do is to try to relate in some or other form the properties of the restricted Lie algebra L with those of the lattice of restricted subalgebras. I'm going to denote, I forgot in the last slide, I'm going to denote this lattice by S of L, okay, subalgebras, well, restricted subalgebras. Okay. So the idea is to relate the properties of these two objects. And we would like to know at which extent the properties of the algebra are determined by these ones of the lattice and vice versa. So this problem has quite a long history. He has been studied in several other algebraic structures. It began, as far as I know, it began in groups in the decade of the 30s, but it also has been studied for modules, for rings, for associative algebras, for Lie algebras, of course, and why not to also study it for restricted Lie algebras. So the properties in which we are going to focus mostly are the distributivity of the lattice of restricted subalgebras and the modularity. So let's begin with distributivity, and well, and we will see. So if I have my lattice S, not now a lattice of restricted subalgebras or a lattice of anything, just a lattice, will be distributive is if this identity is satisfied, okay, for every triple, for each triple of elements of the lattice. The identity just says that the joint of two algebras is distributive regarding the mid. Okay, if I have the joint of A and the mid of B and C, this must be the mid of the joint A and B and the joint of A and C. Okay. This is a definition, but there is this nice characterization by Birkhoff, which says that a lattice is distributive if and only if it doesn't contain these two lattices as a sublattice. Okay, this one is called the diamond, or M3, and this one is called the pentagon, or M5. So we are going to stick to this characterization mostly, and when I present you some examples, we are going to decide if they are distributive or not by studying the lattice and checking if it has these lattices as well, these forms as a sublattice. I think we can really forget about the definition. Okay, so as I said before, the problem of studying these properties of the lattice of sub objects in an object and relate them with the properties of the object began with groups, and in particular distributivity. For distributivity, we have a very nice result given by Ore, which says that the lattice of subgroups of a group will be distributive even only if the group itself is locally cyclic, which means that if I pick any finitely generated subgroup, this subgroup will be cyclic. Okay, or equivalently, if I pick a subgroup generated by two elements, it must be cyclic. So we can see that in particular G must be abelian. This is the characterization. The lattice distributive if and only if group locally cyclic. We can also consider other structures as Lie algebras. In this case, we have this result, even in the 60s, which says that the lattice of subalgebras of a Lie algebra is distributive, even only if the subalgebra is the algebra, sorry, is 0 or it has dimension 1. Okay, so in this case, we've got this trivial result. And let me say briefly why we have it. Okay, the idea is first to focus on dimension 2. If I pick a Lie algebra in dimension 2 with a basis formed by two elements, x and y, it's clear that I will have that the linear span of one element of the basis, x, will be a one-dimensional subalgebra, and also the other one. Okay, I have these two subalgebras, fx and fy, one-dimensional, both of them. But also, if I pick a linear combination of the elements of the basis, I will have again a subalgebra of dimension 1. So as this element, it's going to be in whatever the field that I'm considering, I will have the element x plus y. I have always these three one-dimensional subalgebras, and I'm going to have this diamond, this diamond inside of any lattice of subalgebras. So by the theorem of Birkhoff, we have that the lattice won't be distributive. Okay, and then this is for dimension 2. And if I go to higher dimensions, or we can reduce the problem to find a subalgebra of dimension 2, or we can create an example ad hoc which doesn't satisfy the first identity. So we will have this nice result, okay, that says that the Lie algebras with distributive lattice of subalgebras are in some way trivial. And at this point, we can wonder, okay, this happens with Lie algebras. What have the restricted Lie algebras, which are, at the end of the day, are Lie algebras, which have that make them different, which have that makes interesting the problem to study the distributivity of its lattice of their lattice of subalgebras. Well, we will see it with an example of dimension 2. Again, I pick a restricted Lie algebra, dimension 2, basis x and y. I'm going to have it abelian, and I'm going to consider that x to the p is y and y to the p is 0. Okay, this can be checked easily that it is indeed a restricted Lie algebra. I mean, the P map behaves well with the rest of the structure. But what happens now? Before the linear subspace, the linear span of x, in the scalars of x, form a subalgebra. But now this fx is not restricted, because if I consider x to the p, I got y, which is clearly not in the linear span of x. So now one element itself won't generate, well, the linear span of an element won't be in general a restricted subalgebra. The same happens if I pick a linear combination of the elements of the basis x and y. Okay. If it turns out that the minimal subalgebra containing x, or this alpha x plus beta y, will be the whole L. So the only proper restricted subalgebra which we're going to have is the linear span of y. In this case, if I take y to the p, I got 0, so y to the p is in this linear span, and it is a restricted subalgebra. Okay, so the lattice which I'm going to have is this chain of length 2, okay, which is clearly distributive. So we see that for restricted Lie algebras, this problem won't trivialize as it happened with Lie algebras. And also the next question can say, okay, but you say before that for groups we have this characterization, distributive if and only if locally cyclic. Can we aspire to have something similar for, well, sorry, for restricted Lie algebras? First of all, we should say what we intend by what we understand by locally cyclic. Well, the correspondence in this setting, I have it written, but further on, the correspondence says that it will be a restricted Lie algebra such that can be generated just by one single element. So the restricted subalgebra generated by one element will be the whole L. And let us see this other example here. Again, a restricted Lie algebra of dimension 2, abelian, okay, over an algebraically closed field. I'm going to pick my base field to be algebraically closed. So, as I say, dimension 2, abelian, and now I'm going to define the P map in the following way. X to the P will be y, y to the P will be x. Okay. And this again will be a restricted Lie algebra. One can check it readily. And what have we now? Well, we have, if I pick x, the smallest restricted subalgebra containing x will be the whole L. X to the P is y, and I've got the two elements of the basis in my subalgebra. And the same now with y. Okay, so the restricted subalgebras generated by X and Y coincide RRL. But what happens with linear combinations of the elements of the basis? Well, if I consider any p+1 root of unity, zeta I, and I consider this sum x plus zeta I y, it happens that this element to the p will be just a multiple of itself. So the linear span of this element will be a restricted subalgebra of dimension 1. So, well, the subalgebra generated by this one is a proper restricted subalgebra. And as the characteristic of my field is clearly 2 or higher, this p+1 will be 3 or higher. So I'm going to have at least 3 subalgebras, 3 restricted subalgebras of this type. And I'm going to be able to pick this diamond as a sublattice of the lattice of restricted subalgebras. So my algebra, my restricted Lie algebra, the lattice won't be distributive. But I said here that the subalgebra, the restricted subalgebra, generated by X or by Y is the whole L. And this is exactly what I was saying before. That means that the restricted subalgebra is cyclic, okay? It can be generated by one single element. In this case, X or Y. X or Y. So my restricted subalgebra is cyclic, but its lattice is not distributive. So we also won't have this equivalent, we don't have an equivalent characterization to the situation in groups. So let's explore another structure. What about modules? If I pick a ring and I consider a ring R and I consider a left R module M, we have this result due to Camillo, which says that the lattice of submodules is distributive if and only if every time that I pick a submodule N, the quotient M by N won't have two isomorphic simple submodules, okay? And this result is not as nice as there were the previous ones, as easy to state, but it will be the one in which we can base for giving a characterization for restricted Lie algebras with distributive lattice. Okay, the key point is that we're going to be able to see restricted Lie algebras with distributive lattice as a left module over a certain ring. So let me speak a couple of minutes about our tool, which is the skew polynomial ring, which already appeared last week in the talk by Suzanne, but let's review it for a couple of minutes. Okay, the underlying subspace of this skew polynomial ring will be the same as the usual polynomial ring, okay? My linear combinations of this variable t, powers of this variable t, and by elements of the field multiplied on the left. And as you may recall, this ring won't be commutative, as if I want to multiply the variable t by an element of the field, but on the right, not on the left, I've got this formula, okay? When this sigma, which appears here, is an endomorphism of the field, and this delta, which appears here, is a left sigma derivation, which means that it's a linear map from F to F, which satisfies this identity for the product. Okay, delta of AB will be sigma of A delta B plus delta of AB. In our case, remember that we are dealing with fields of positive characteristic. So we are going to make precise choice of this endomorphism sigma and this derivation delta. As an endomorphism, we are going to take the Frobenius endomorphism of the field. Okay, and as a derivation, we are going just to take 0. So this skew polynomial ring will simplify, and we will have we will denote it by F, T, and sigma. And we will have just this simpler rule of multiplication. T plus alpha will be alpha to the p, the image of alpha by the Frobenius endomorphism, times the variable. Okay. Unless we have that every element of the field is the same as p power, we will have that our ring is not commutative, and this will complicate a little bit things, but we will see in time. Okay, so why we need to, or we're willing to consider this ring? Well, if I have a restricted Lie algebra, which is abelian, I just have to care about the product by scalars, the sum, and the P-map as the bracket vanishes. So this P-map can be thought of like the action of the skew polynomial ring, yes, this skew polynomial ring over L, defined this way. The action of the variable t on an element x will be x to the p. Okay, one can check that this is well defined and the properties hold and everything works. And each time that I have an abelian restricted Lie algebra, I have this extra structure of left module over this skew polynomial ring. Okay, and which is most interesting is that the lattice of restricted submodules, considering this L as a module, is the same as the lattice of restricted subalgebras. So we are going to be able to study our object of study, this lattice of restricted subalgebras, by going to the lattice of submodules. Okay, but the problem, if you want to say it so, the problem of this setting is that we need an abelian restricted Lie algebra. Okay, for non-abelian restricted Lie algebras, this doesn't hold. But the good news are that if I have an arbitrary Lie algebra which has a distributive restrictive or a distributive lattice of restricted subalgebras, then the L will be abelian. Okay, and as an abelian Lie algebra, then I can consider its structure of left module over the skew polynomial ring. So now with these ingredients, I can state my main theorem, that is that the lattice of restricted subalgebras will be distributive even only if L is abelian, and I here use Camillo. For every restricted subalgebra H, the quotient L times A, L by H, does not have two isomorphic minimal restricted subalgebras. Minimal in the sense that they don't have any proper non-zero restricted subalgebra, okay? Minimal in the lattice. The implication to one side is clear. I already said that distributive, lattice distributive implies L abelian, and the other condition is just applying Camillo, and the other way around, well, it's also immediate by this structure and by the theorem of Camillo. So we have this theorem, which is not extremely nice to state or to use maybe, but which will allow us to obtain nicer consequences if we ask for additional conditions, okay, for additional hypotheses. For example, I have a restricted Lie algebra, but I ask the field to be perfect. In this case, we have a structure theorem for abelian restricted Lie algebras, and we have that if the lattice is distributive, then will be locally cyclic. Okay, we recover in some sense the result that we have in groups. And also, if you are wondering about the converse, if now I take the field furthermore to be, in addition to be perfect, I choose it to be FP, the field of P elements, now I have the converse. But why is this? Well, in this case, if I pick FP, here the Frobenius endomorphism is just identity, so the skew polynomial ring will be just the usual polynomial ring, which is commutative, which is a principal ideal domain, which is a unique factorization domain. And I'm going to be able to imitate in a certain sense the arguments of Ore, and I will have also this implication in the other way. Okay, so in this particular case, we recover totally the results for groups. It's worth to say that my our not nice result, this one. Okay, if we translate it to the setting of groups, we will have that well, this in groups, this will be equivalent to distributive and leaf localization. But in restricted algebras, it won't unless, well, we have these additional conditions. Okay, so what else? I've considered F perfect. I've considered the most restricted case FFP. What about algebraically closed fields? Well, in this case, we have a nice result also, which says that the lattice of restricted subalgebras is distributive if and only if L is isomorphic to a restricted subalgebra of this pink algebra here. Which is this algebra? It will be a direct sum of a one-dimensional restricted subalgebra, okay, generated, well, yeah, generated a linear span of one element x, such that x to the p will be a non-trivial multiple of it, and this restricted Lie algebra, which I denote here by C sub infinite, and which is it? Okay, this will be the direct limit of some kind of restricted Lie algebras, Cn, which are the cyclic subalgebras, the cyclic, restricted Lie algebras generated by one penilpotent element, or in other words, which are the quotients of the free cyclic restricted Lie algebra by this subalgebra here. X, the one generated by a certain power of a certain p power of the element, the generator X. Okay, and which aspect have the restricted subalgebras, or well, the restricted subalgebras, the lattice of restricted subalgebras of this algebra here? They will have the form of a ladder. I like to call it a ladder. And it is in this way, it will be easy to detect the subalgebras if the lattice is distributive. The only option that we have is that we have this ladder. And at this point, you may ask, okay, you're talking here about a ladder, which is kind of a simple example of simple lattice, but there is one example of a simple lattice, which is even simpler than one ladder, and it's a chain. Okay, just one side of the ladder. So what can we say about restricted Lie algebras which have this one? We'll have a chain as a lattice of restricted subalgebras. Or if we want to be a little less ambitious to begin, we can ask when a restricted Lie algebra has just this lattice of subalgebras, okay? This chain of length 1, or if you analyze the lattice, you can say, okay, when a restricted Lie algebra L, which will be this upper point, doesn't have any proper restricted subalgebra different from 0. Okay, so which are the restricted Lie algebras without any non-zero proper restricted subalgebra? And not really surprisingly, we've got this result. Note that if I have this lattice, okay, if I pick an element, a non-zero element, the subalgebra generated by it must be the whole L, okay, as there are not other proper restricted subalgebras. So my algebra will be cyclic, and in particular abelian. And once again, the skew polynomial ring, this structure of modulo over the skew polynomial ring comes to help us. And we can say that we have exactly this situation if and only if my Lie algebra is the quotient again of well, the cyclic will be the quotient of the free cyclic restricted Lie algebra. By what? Well, in this case, by the restricted subalgebra generated by the action of a skew polynomial over X, and such that this skew polynomial is irreducible. Okay, we can decompose it into a product of other two skew polynomials. And once we have this, if we stick to the algebraically closed case, we have a nice consequence, and is that my restricted Lie algebra won't have any proper restricted subalgebras if and only if the dimension of the algebra is one or 0, less or equal than 1. And this allows us to recover, in a way, the kind of the fundamental theorem of algebra for skew polynomials. I mean that a skew polynomial over an algebraically closed field will be reducible if and only if it's linear. This can be obtained by direct calculations, but this is like a fancy way of proving it also by means of restricted Lie algebras. Okay, so I said that this result was not really surprising, as if we go back to the setting of groups, we will have this equivalent result that a group has no non-zero proper subgroups if and only if it is isomorphic to a quotient of set by this subgroup, normal subgroup, generated by a prime element. Okay, so if we translate this into the setting of restricted Lie algebras, we will have exactly the result which I have just presented. And one can say, okay, this so the situation in groups and in restricted Lie algebras in this case happens to be the same. What about chains? Because if I have of chains of arbitrary length, because if I have a group, I still have this result which says that its lattice of subgroups is a chain of length n, if and only if J is the group, is isomorphic to now a quotient of set by this subgroup generated by a power of n, a power of a prime element B, and the power is the same as the length of the chain. Okay, so a naive approach which would say, okay, so now if I go back to restricted Lie algebras, I can have the same result. I can have that the lattice of restricted subalgebras is a chain of length n if and only if L is isomorphic to this quotient of free cyclic restricted Lie algebra by the subalgebra generated by the action of a power, the nth power of an irreducible skew polynomial acting over X. Okay, this would be the translation of the property of the characterization in groups. But now this characterization doesn't work. Okay, this is not true. So let me show you some examples to convince you that this is really the situation. For example, I'm going to have this field of characteristic 2, the field of 4 elements, okay, which are going to denote by 0, 1, A, and 1 plus A. 1 plus A, sorry. I'm going to have this model here, and I'm going to consider quotients of the free cyclic restricted Lie algebra by powers of an irreducible, by subalgebras generated by the power of an irreducible skew polynomial acting on L. In the sphere case, I pick I don't know where is my mouse. Well, in the first case, the case on the left, I pick the polynomial t plus 1, which is irreducible, and I consider the second power, okay, t plus 1 to the square, and without much effort, one can check that the lattice of restricted subalgebras will be the diamond. So this is not distributive and it is clearly not a chain. But if I choose another skew polynomial, the one in the middle, t plus a plus 1, which is irreducible and consider it to the square, now I do obtain a chain as a lattice. But also in the example of the right, I consider the product of two irreducible skew polynomials but different between them. I would expect in my naive approach to have kind of a rhombus. Well, yeah. But I have still a chain. So what is the reason of this kind of pathological behavior? Well, it is that my skew polynomial ring is not commutative and it won't be a unique factorization domain. So I'm going to be able to decompose these products on different ways, in some cases, in some others don't. And I can have different lattices. So a way to solve this problem could be considered as the base field, the field of P elements, in which we already saw that the skew polynomial ring is just the usual polynomial ring, is commutative, and everything is beautiful and works perfectly. But this case is very restrictive. So another solution or another situation that we can consider to understand a little bit these chains is a situation in which L is p-nil. What I mean by p-nil, okay, I say that a restricted algebra is p-nil if every of its elements is p-nil potent. And what means that it is p-nil potent is just that there exists some natural n such that if I apply the p-map n times to x, oh, here's my mouse again. If I apply the p-map n times, I got 0, okay? So for this kind of restricted algebras, I will have that the lattice of restricted subalgebras is a chain if and only if n is isomorphic to algebra Cn, which appeared before, but I'm going to recall its definition because it's just the quotient. I presented before by the quotient of the free restricted algebra by subalgebra generated by a certain p power of the generator x. But this can also be written as I have here. This the quotient by the restricted algebra generated by the action of t to some power n on the generator x. And clearly t is an irreducible skew polynomial. So in this p-nil case, we kind of recover this that naive approach that worked in groups and that I presented before. Okay, well, this works also for infinite dimension. Okay, we have an infinite chain if and only if L is this C infinite that I presented before, the direct limit of the Cns. And also, it's interesting that this is in this p-nil case, this is the only choice that we have to have a distributive lattice or restricted subalgebras. Okay, these two equivalences are also equivalent to the distributivity of the lattice. So there are not other configurations of the lattice in p-nil case which are distributive. Well, just the chains. Okay, so I think this is all about distributivity. Let me now speak briefly about a related condition on the lattice, which is to be Boolean. We will say that a lattice is Boolean if it is distributive and also it is complemented. And what do I mean by complemented? I mean that there exists a maximum element denoted by 1, a minimum element denoted by 0, and also such that if I pick an element x, whatever, there will exist another element y, such that the mid of these two elements is 0, and the joint of these two elements is 1, is the maximum. Okay, the joint the maximum, the mid the minimum. Okay, so this is to be Boolean, and also once we have the characterization, that first theorem that we presented, which was not nice, well, not so nice. once we have this characterization of distributive, it's easy to, well, it's not difficult to obtain also a characterization for Booleanity, which says that L, we have a Boolean lattice if and only if it is a direct sum of pairwise non-isomorphic restricted algebras. Each of them doesn't have a non-zero restricted subalgebras. Again, this corresponds nicely with the situation in groups, but I won't go into details now. So I promised at the beginnings of the talk that I will speak about mainly about two properties, distributivity and modularity. So let's begin, let's say something about modularity. Okay. When is a lattice modular? No, we have first to define it. And the modular lattices are the ones which satisfy this identity. Broadly speaking, if I have a joint and a mid, I can put the parentheses in any way I want to. Okay, this joint will be the same as this mid. I have to ask that A is a less or equal element than C. In our case, we have that a subalgebra is contained in the subalgebra A has to be contained in subalgebra C, but well, this is the definition. And again, we have this characterization of Virchow, which says that a lattice is modular even only if it doesn't contain the pentagon M5 as a sublattice. Recall that in the case of distributivity, we have that the characterization of Virchow said that a lattice was distributive even only if it didn't contain this pentagon on this or this lattice or the diamond, sorry, as a sublattice. So in the case of modularity, it only appears here the pentagon, so it's clear that a distributive lattice in particular is modular. Okay, and what is the situation, historically speaking, what is the situation of modularity? Well, it's, for example, the lattice of, in a vector space, the lattice of subspaces will be modular, the lattice of submodules of a module will also be always modular. The lattice of normal subgroups will be modular. Okay, what happens with the lattice of subgroups? Well, there is a characterization. We have that the lattice of subgroups is modular, even only if some classification, which I don't want to detail. Just let me say that this is quite more complicated than the characterization for distributive lattices. We can differentiate between finite groups and infinite groups. And in the case of infinite groups, one kind of groups which appear here are the Tarski groups and related groups to that, extended Tarski groups, which are, roughly speaking, infinite groups in which every proper non-zero subgroup is simple, okay? And these groups are not, we know that they exist, but they are not completely classified. So the groups with modular lattice of subgroups are classified up to this classification of Tarski groups. Okay, and in Lie algebras, what happens in Lie algebras? Before we had a very trivial result with distributivity, but now things get more complicated. Let me begin with this locally finite dimensional case. I mean, every finitely generated subalgebra will be finite dimensional. We have this characterization by Lashik, which says that the lattice of subalgebra, of a Lie algebra is modular if and only if the algebra is abelian, has dimension 3 and is simple, and not isomorphic to SL2, or it is almost abelian. This is just a piece of notation. An algebra is almost abelian if it can be, if it is the sum of an abelian ideal plus a one-dimensional subalgebra, which acts as the identity on A, okay, on the abelian ideal A. Okay, and what happens if we go to the general case? We forget about this locally finite dimension, and we go to the general case. Well, we have also that if the lattice is modular, then L can be abelian, almost abelian, three-dimensional simple not isomorphic to SL2, or we can have that every two elements, every two linearly independent elements, generate this infinite dimensional Lie algebra, which is kind of the analog of a Tarski group in the context of Lie algebras. An infinite dimensional Lie algebra in which every proper non-zero subalgebra has dimension 1. The problem here is that we don't know if this Lie algebra exists or not. So this result is kind of tricky. And if we go to the context of restricted Lie algebras, we will have again the same problem. If we want to tackle the problem with generality, we expect that this problem is likely that this analog of restricted Lie algebras, this analog of Tarski groups in restricted Lie algebras appear. And once again, we don't know if this restricted Lie algebra exists or not. Although there is a conjecture by Pasha-Osmanovic which says that it doesn't, but it is just a conjecture. So first note to deal with this issue, restrict to finite dimension. But also, as you could see before, both in the context of groups and in Lie algebras, the situation is considerable. It's quite more complicated than it was for distributivity. So we needed to take some more restrictive hypotheses, and we arrived to this conclusion that if we have a restricted Lie algebra of finite dimension over an algebraically closed field of characteristic greater than 3, okay, we have that if the lattice of restricted subalgebras is modular, then we can have three options. L is abelian, L is almost strongly abelian, which is well, the correspondence, the analog of almost abelian Lie algebras, and it means just that, well, the algebra is almost abelian, is a direct sum of an abelian ideal A plus an element as the algebra generated, the restricted subalgebra generated by one element X, which acts as identity on A. And also, what about the P-map? Well, the P-map vanishes on A and is identity on X. Okay, so this case, we have these cases: L abelian, L or almost strongly abelian, or L is nilpotent of class 2. When at this point, one can wonder, what about the converse? Does the converse hold? Well, it's clear that if L is abelian or is almost strongly abelian, it does hold. Okay, the abelian or almost strongly abelian restricted Lie algebras have a modular lattice of restricted subalgebras. But if we go to the third case, the two-step nilpotent, we see that this converse does not have to hold. And I included an example. Pick a four-dimensional restricted Lie algebra. Okay, basis X, Y, Z, and W. And I define it to be, okay, Y will be the P power of X. And the P map on X is Y. And the P map on Y, on Z, and W will be 0. And also the bracket. Well, clearly the bracket with X and Y must be 0 to preserve the conditions of a restricted Lie algebra. I will take the bracket of X and Z to be W, and this will be the only non-trivial bracket. Okay, Y and W belong to the center of the Lie algebra. Again, it can be checked that this is a restricted Lie algebra, and it is two-step nilpotent because if I consider the derived subalgebra, L times L, I got just the linear span of W, but the linear span W belongs to the center, is here. So if I consider this again, the this bracket again, I will have 0. Okay, so L is two-step nilpotent, but we'll see that it doesn't have a modular lattice of restricted subalgebras. Let's see. I can consider a subalgebra native by X, which will have, well, X and Y. But it's abelian, it's cyclic abelian. In any case, it will have W. So the restricted subalgebra generated by X and W properly contains the restricted subalgebra generated by X. And it here it is not set. So this is not the whole algebra. Okay. On the other hand, sorry, set, the element set, the linear span of it is a restricted subalgebra as the p power of set is 0. So this is another restricted subalgebra. And if we consider the joint of the one generated by X and the one generated by set, sorry, we will have X, Y, we will have Z, we will have its product, W, so we will have the whole algebra. And these considerations define define this sublattice in the algebra, in the restricted algebra, which is the pentagon M5. So by the Birkhoff's characterization, we know that the lattice is not modular, but the algebra was nilpotent of length. So, well, we have this counterexample, and this was all that I wanted to tell you. So many thanks for the attention. And if you have some question, I will try to answer it. Thanks.
Thank you very much for your presentation. Indeed, if there are any questions, please, now is the time to ask them. Well, it seems that right now there aren't any questions, but possibly there will be some later. I would like to thank you once again for giving your talk. Thank you very much.
Thank you to you for your attention. Thanks.
Thank you.